The recording is in progress. Welcome to our class today, Thursday, February 10, 2022. Our class today will start with the material that will not be included in the midterm. Again, I explained yesterday what will be included in the midterm material, which is handout 1, 2, 3, 4, 5, and 5A. In addition to that, like the study guide for pumping lemma and the class note 1 to 7. So any class note connected to the handout is also included. Today, we will work with handout 6, and this is not included in the midterm material. Clear, guys? So today we will study handout 6 and the class note number 8. Those are not included in the midterm exam. Those, and also in assignment 1, it's not included. Those will be included in the final exam, and however, the midterm exam is included in the final exam, but the more weight will go toward the topics that was not covered in the midterm. Any question regarding midterm material, guys, before we proceed with handout 6? Questions? Okay, let's start. Can you see my screen? Thank you, Gareth. Okay, so we studied the first level of computation using NFA, DFA, and regular expression. Yesterday, we go to an upper level, which is context-free grammar. And we see that context-free grammar can describe some languages that they are non-regular languages, like 0 to the power n, 1 to the power n. Today, we go further step in the hierarchy, Chomsky hierarchy. Let me open handout 5. And yesterday, we touched base with Chomsky hierarchy, and we said that regular language is the basic level, the first level, then the other level that contain the first level is context-free grammar, which has context-free grammar and push-down automatas. Today we will study the second part, which is the push-down automata. And we said that the context sensitive, it's beyond our scope, and recursively enumerable, we will study only one topic, which is the Turing machine. You see here, this will not be studied, not studied, not studied. So, our class today, push-down automata and pumping lemma for context-free languages. We'll see more advanced level of pumping lemma, that we split the string to 5 parts instead of 3 parts for regular expression. So be careful when you answer the question. In the midterm, just the pumping lemma was studied. But in the final exam, you have to be careful when you read the question. It's regarding regular expression or languages, or the pumping lemma for context-free language. There are some languages, they are not context-free also. We will see. I'm not sure, maybe today we'll not touch base with that, maybe next Wednesday. Push-down automata. Introduction. Let's recall our now classical example that the language L equals 0 to the power n, 1 to the power n, where n is greater or equal to 0. We use the pumping lemma to prove L is not regular. Then we give the context-free grammar that generate this language. S will give us the production rule, saying S will give us 0 as 1 or epsilon. Recall the grammars like a recipe for generating a language. We talked about these concepts yesterday. On the other hand, automata are devices for recognizing language. In this lecture, we are going to look at the class of automata for recognizing context-free languages, and we call it push-down automata. There are many other models, but in this course, we will study the push-down automata. So, what is the push-down automata? Consider an NFA reading input AABB. In this example, it starts at the left at the A and moves to the right one symbol at a time. So if we have an NFA, we will read the A, then we move one step. We start at the left, then we move one step to the A, then B, then whatever else we are reading. So this will lead us that a push-down automaton is essentially a non-deterministic finite automaton with the added ability to read and write from a stack. So here at this level with push-down automata, we start seeing the concept of a stack. Are you guys familiar with the stack? What is the stack concept? Okay, Brandon, unmute your mic and tell us, what is the stack concept?
It's like last in, first out.
Yes, thank you, Austin. LIFO. Yes, it's a memory location that the last symbol will come onto the stack, will be the first symbol will come out of the stack. And we call this operation when we are adding a symbol to the stack, we call it push. And when we are getting it out or any symbol out, we call it pop. So push, we adding thing to stack, pop, we are taking that thing to the stack. And it would be the last thing that we added. So what is a push-down automaton? A push-down automaton is an undeterministic finite automata, NFA, with the added ability to read and write from stack. Each time it reads an input symbol, it can also read the top of the stack and do a stack operation. What are the stack operation? Push and pop. Push we adding, pop we are getting out. So the formal definition, a push-down automaton is a 6 tuple, which has a Q, which is finite set of states, sigma, which is an input alphabet, rho or tau, they call it, I'm not sure, stack alphabet, then delta, which is Q times alphabet with epsilon times tau, I think, with epsilon, which will give us P, Q times tau with epsilon, transition function, Q naught, which belongs to Q, which is starting state, and F, which belongs to Q, which is a set of accepted state. If you look, you will find it's like an NFA, but we add here the stack alphabet. We add here the stack alphabet. And it's also with the transition function, it will give the tau with epsilon. This is for pop, we will use it. We will see. From the definition, we see that a transition involves the current state, the current input symbol, and the current stack symbol in the top of the stack. So here, if you see, we are adding. So it has the current stack symbol, on the top, and next state, what is the next stack symbol, and the current input symbol. So we have the current input symbol, the current stack symbol, and next state, and a next stack symbol. This is what we added. So it's the same as NFA, but we add the stacks things. So A, B, then C, which can read reading A on input and B on top of the stack, replaced B with C. This is how we read it. We will read A as an input. B is in at the top of the stack, and replace B with C. This is how we read it. A equal epsilon, we make the transition without reading an input symbol, like in an NFA. If A is equal epsilon, then we'll do the transition without reading any new input symbol. B equal epsilon, we make the transition without reading or popping from the stack. Then A is epsilon, we will make the transition without reading an new input symbol. If B, the second thing, is epsilon, we will make the transition without reading or popping from the stack. If C is epsilon, we make the transition without pushing anything to the stack. Now with the example, it would be clear. Pushdown automaton, the stack. Using the notation, we can define a set of stack operation. Push, pop, or replace, or do nothing. The main thing, two operations are push and pop, as I mentioned before. But also we can replace the top symbol in the stack. So X epsilon Y, if you read X in the input, push Y. XY epsilon, if you read X on input and Y on the stack, push epsilon. Replace X, Y, and Z, if you read X on input and Y on the stack, push Z, which will be replaced Y with Z. Do nothing, X epsilon, if you read X on input, do nothing to the stack. Bottom of the stack, technically the stack is a string and is initialized as epsilon. So the first thing normally we put in the stack is epsilon. Depending on application, you may wish to push an explicit bottom of the stack when the automaton starts. Some in the programming languages, if you remember, some instructor, they use the hash to give us a notation that this is the end of the stack. Recall our language L, 0 to the power n, again to our example, 1 to the power n is greater or equal to 0. Let's draw a push-down automata that recognizes this language. Here, what we will need to do, mark the bottom of the stack, so we will know if when we encounter it later. That done. Start pushing the zeros into the stack. As soon as you see a 1, start popping items off the stack. Pop one item for each one you see. If the stack becomes empty upon seeing the last one, then you saw equal zeros and 1, therefore accept. So with this concept, we will start working with the stack. Once we see 0, with each 0 we do a push. How we will know that the number of zeros is equal number of ones? Here we have a memory, but it's still at the basic level. We cannot go left or right to count. We don't have memory to counter as a counter. So how we will do this? We'll push zeros. Each one we will see will pop a 0. If Once ones are done, I don't have no more ones. If the stack is empty, that means that the number of zeros is equal to the number of ones. Then we will accept. If not, then we will reject. Clear, guys? Questions still here? Okay. So, putting this together, we have at Q1, start, mark the bottom of the stack. Q2, read through zeros. If 0 on input, push 0 to the stack. And keep doing that. Once we're done with the zeros and we start reading ones, if 1 on input, pop 0 from the stack. Read through ones. If 1 on input, pop 0 from the stack. Is bottom of stack? If yes, then accept. Who can tell me why we make then the Q1 also as final state? Why we mark a Q1 as final state? Empty string. If we don't have zeros and 1, we have empty string, then we should accept. No number of zeros, no numbers of 1, then logically the number of zeros is equal to number of 1, which is equal to 0 as a count. That's why if we receive an empty string and we don't have zeros and 1s, then we can accept also. Okay, or rewritten the transition as the following: start, epsilon, epsilon. This is the hash sign. Wait, we just see it. The hash sign, the dollar sign. So this one is the symbol that will tell you that we reach to the end of the stack. So this is the first symbol, we push it. As I told you, some programming languages, we used to push the hash number or the hash sign. Some, they will use dollar sign. If you want, you can use A, capital, whatever you want. Explanation mark, question mark, add symbol, whatever. But the language should know that this means that it's end of the stack. Okay. So at the beginning, we push the dollar sign, which is the bottom of the stack. Then we start reading a 0. We push zeros to the stack. Once we receive a 1, we pop a 0. That means with the after the arrow is epsilon, that means it's pop. If the epsilon is before, which means it's push, then we'll keep popping the zeros. If we reach that, we have no more input, and only we have the the dollar sign. Then the number of zeros is equal to the number of 1. Then end and accept, which is a final state. So what would happen if we have more zeros than 1s? Then there will be zeros on the stack when the computation stops, and thus we won't be able to accept the state Q4. More 1s. If we have more 1s than zeros, as soon as we run out of zeros, we will see the dollar sign symbol and the transition to Q4. However, if there are 1s remaining, which means that the number of 1s is more than the number of zeros, then we will stay at Q3 because we'll go to the dead state. We cannot pop a 0, so we'll stay here. Out of order zeros and 1, same as before, as per the transition, there is nowhere else for the computation to go, so it also proves and dies. So it will go to the state, either here or here. Okay, equivalent of push-down automators and context-free grammars. A language is context-free grammar if and only if, again, if, that means if and only if there exists some push-down automata that recognize it. Same if you remember about regular languages. A language is a regular if there is an NFA or a DFA that, or there is a regular expression can recognize it. To prove this, we will follow the same strategy when we prove the equivalence of a DFA and an FA. The proof for every CFG generating language L, there exists some PDA recognizing L. So if you go to the CIPSR, the other textbook, there is a proof using pumping lemma or using lemma for in 2.21. The proof for every PDF recognizing L, there exists some CFG generating L, and also it's 2.27 in CIPSR. If you want to look for the proof, I'll not ask you about it. PDF in this context. Oh, sorry, it's a PDA. PDA. Maybe Professor Essex has a typo. It's a PDA. Same guys in assignment 1, question 3, there is a letter E, it is epsilon. It is epsilon. It's a typo also. Assignment 1, question 3, I'll send an announcement, it's epsilon. Now, we will stop here. We'll not have the pumping lemma for context-free languages because, as you see, we will start dividing the string using the parse tree, so it will be a bit complicated. And then we'll have uvi to the power I x to the y to the power I z. So we'll divide it into 5 portion. So we'll partition the string to 5 parts. So this we start with it because it will take, it need time. So we'll start with it on Wednesday, but we'll cover the part that connected with what we explain for today. Pushdown automata, epsilon and FA plus a stack. This is what it is consists of, which is epsilon with non-deterministic finite automata, plus we have a stack now. The combination of epsilon and FA and the stack is called pushdown automata. Stack has 2 operations, push and pop. Push will add an element to the top of the stack. Pop removes the topmost element from the stack. Stack is a linear data structure that you can access only from one end. We cannot go to the bottom of the stack immediately. Only the topmost element can be accessed at a given time. To access an intermediate element, all elements above it must be popped. A pushdown automata has an input tape, which is a basic type of memory. If you remember, I don't know, guys, for me, we are very familiar. Do you remember the old like recording machines that when we listen to the songs before the CDs, the normal tape? Do you remember that? Okay, sounds good. So if you want a certain, in the normal tape, assume that you have a recorder that can just go forward, cannot go backward in the tape. So this is the pushdown automata. It's an input tape that can be accessed from one side. We cannot like forward and reward, backward. We can just go forward. So a pushdown automata has an input tape, a finite set of states, and an unbounded stack input tape. So from this side, we can access. We put A1, then we'll move to A2, then we'll put AI, then AN. In the stack, if you wanna see that this is the first bottom element, and this is X is the most top element. This is the pushdown automata. At any given point of a time, the pushdown automata PDA is in some state P, reads some input symbol AI, access the topmost element of the stack, we call it X. The PDA at this point can move from state P to state Q, can change the topmost element of the stack X to Y, or can pop it, or can push a new element. This is represented as P AI X will lead us to Q and Y. This is another form of representing the operations. We allow stack to have a different alphabet, usually denoted by gamma. It's gamma. It's gamma. This is the capital, like, you know, in English, capital letter and the small letter. In the small letter, we know the gamma, but like a capital letter, it's represented like this. Given an input W, the PDA at any given instance does the following: reads AI from W, where AI belongs to the alphabet with epsilon, goes from state P to Q, replaces the topmost element of the stack X with Y, where XY belongs to gamma epsilon. What does it mean for X to be epsilon? Which means pushing Y into the stack. Y to be an epsilon, pop out X from the stack. Okay. Formal definition is available at handout number 6, slide 6. I'll not repeat it again. Due to non-determinism of the PDA, there can be multiple transitions on the same tuple, P, X, AI, and X. Transition denoted as P, Q, A, I, X, then Y. A PDA P, Q, the same as we get in the sun, is said to accept a string W belongs to alphabet star or to sigma star if there exists a sequence of symbol A1, A2 to AM where it's belong to the alphabet, state R0, R1 to RM where belong to the Q, which is the set of states, string S0, S1 to SM that belong to gamma star, such that W equal A1, A2 to AM full string, R0 equal Q naught, and S0 equal epsilon initial condition. For each I, for every I, if RIY belong to delta RI minus 1 AIX, then SIYT for some T belong to the gamma star, and XY belongs to gamma epsilon. Transition condition, how we will do the changes. Then RM belongs to F, which is the accepted state. So before the step, we have X and T. After the step, we replace X with Y, then it will become Y and T. Example. So here, the first example, we will repeat it with a table to let you understand each single step. Given the PDA of the language, L equals 0 to the power n, 1 to the power n, where n is greater or equal to 0, we start with the Q naught. At the beginning, epsilon, epsilon, here hash. I use hash, same as used in data structure. In the handout, we use $sign. You can use whatever you want. At the Q1, 0, epsilon A. If the second one is epsilon, what does that mean? Push a 0. Then epsilon, 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 do nothing. Once we start with 1, pop 1. When we see the epsilon after that, mean it's pop. Then when we have epsilon and the next symbol is hash, then epsilon and go to the final state. So for example, if we have O to the power 2, 1 to the power 2, which is 0, 0, 1, 1. So at the beginning, we start at the Q node. We will have epsilon, and we push to the stack the hash sign here, based on this step. Okay. Then we will read the first 0. Then we have 0, epsilon, A here. That means push A and hash. We can push a 0. We can push a B, whatever you want to represent this. Then we read the second 0. Then we have to push an A. Then we stayed at Q1. Then we'll have A hash in the stack. Then we'll have epsilon, epsilon, epsilon. We do nothing. We still at, but we move to Q2 with this transition, with epsilon transition. We move to Q2 because we'll start reading once. Okay. Then we stayed at A. We have 2 zeros here. Then with the first one, we will pop, because the epsilon is the end one. Then we'll pop an A. Then we'll have A hash. Then with the second one, we'll pop the second A. Then we'll have a hash. Here, if we have an epsilon, nothing to input, and we have a hash, then we'll pop out the hash, and the stack is empty now. Then accept. Hash mean the bottom of the stack, same as $sign example in the handout. Okay, Tammy? Good. So you can use any symbol, as I told you, at, question mark, whatever you want. But normally, most of the book, they are using the $sign. Most of programming languages, when we study the data structure course, they use the hash symbol. That's why I use the hash symbol here, which means the bottom of the stack. No more symbols in the stack. Okay, let's take with the same example here. Let's take if we have O to the power 2 or 0 to the power 2, 1, which means 0, 0, 1. This should not be accepted, but we will see. We Q naught, we have epsilon. Then with epsilon, epsilon to hash, we'll push a hash on the stack, which is the bottom of the stack. Then we will read the first 0, we'll push A. We read the second 0, we'll push another A. Then we'll have in the stack A hash. Then we'll have the epsilon transition to move to the ones. We read the first one and we pop an A. Then we'll have A hash and the state. We freeze here. So string is not accepted. You can solve it for O1 square and see. You can solve it. So let's make it a volunteer question for next Wednesday. Okay, let's take a more complicated example. Let's take a more complicated example. If we have a language L that has A to the power I, B to the power J, C to the power K, where I equal J, which means the number of A's equal number of B's, and or J is greater or equal to K and less than 2 Ks. So we have here, the condition will take us to 2 branches, either. So the first branch, we will consider that I equal J. With the second one, with this one, it would be almost the same as this one here, because the number of zeros is equal to the number of ones. But what if we took this one, that the j is greater or equal to k, whatever the I, we don't care about I, and here we don't care about k with the same one, but with the second branch, j should be either equal to k or as maximum equal to double number of k. So how we will start? We start with epsilon hash to start with the stack, and this is the bottom of the stack. Then we'll take a, we'll read the a, epsilon a, we'll keep pushing a's. Then we'll move with epsilon to start reading the b's. At each b, we'll pop an a to make sure that the number of a's equal b's. Then with c, we'll keep epsilon. We don't care about c, how many c's we have. Then we will end and go to the accept state, which is almost the same, but we add the step of c, which however we have c's, I don't care. I just concentrate about the number of a's and number of b's. The second branch here is about this condition. Then we read a with epsilon. We don't push anything to the stack because I'm not care about a's. Once I'm done with a's, I'll move to start read b's. And here I have two cases. As minimum, the number of b's should equal number of c's, at least. Or as maximum, should reach to the double of k. What shall I do? So here with b, I keep pushing b to the stack. Then I'll move to c with epsilon. And here, either I pop 1b here and move, or I pop 2b's. Do you understand this step? Once I reach to the bottom of the stack, then I would accept. Why we make this? Because the number of b's at least should be equal to the number of c's. So if it's equal, with each one we'll pop a one. But what if I have more c's, or sorry, if I have more b's? What I will do then, at some steps I'll pop 2b's till we reach to the empty of the stack. Then we will go to the end. Question about this example? Is a new stack created for each epsilon transition? You know, as a part of non-determinism, we should study each path in parallel, right? You remember the non-deterministic, that we have multiple paths that are running concurrently in parallel. So we'll have a stack here and have a stack here. Yes. Of course, the stack in here is different than the other one. Yes. Because each path will have its own stack. And it's either will lead us to accept or to dead state, which is reject. Questions? Okay, let's have another example. Assume that we have a language L2 that consists of a string W, which belongs to A, B star. W equal the reverse of W. You know this thing. Like A, B, A. If you read it from each part or from each side, it's would give the same string. A, B, A, B, A, B, whatever. So we start with the epsilon, we'll push the hash, then we'll take the Q push here, and it will take B and push the epsilon, we'll put B, then we'll put A. Also here it will push A or push B at the beginning. With epsilon, we'll go to start popping to read it as the same, because you know, the last in the stack will be the first out. That's why it's the stack, once we push a string, when we pop it, it will give us to the reverse one. But it should be the same. They should be equal. So here with A, we'll push an A. With B, we'll push an a B, or pop an a B. Then once we reach to the hash, we'll go to the and accept state. So we stop here today. If you have any question, ask. If you don't have any question, you are free to leave, because I know that you have, some of you, they have another classes right after our class. So if you have a question, stay and ask. See you next Wednesday. Thank you, Samuel. Have a good day and see you next week. Bye for now.